Let's go over our assignment that we handed in yesterday and just hand it back to you here just now here. Electricity mini assignment, 19 questions. Try to get through this whole thing this class. Starts off with question number 1. I gave you the answer to question number 1 accidentally, but we're going to go over it anyways because it's a good question. It's, in fact, a similar question to one of the ones that we had on our momentum mini assignment. On our momentum mini assignment, we had a collision between two cars, and we were asked to draw the force vectors, the impulse vectors acting on both of those cars. And at the time, I told you that, well, if object A applies a force on object B must apply an equal and opposite force on object A. And if the forces are the same, then the impulses have got to be the same as well. Well, here, we don't even have to go to that next step and make the translation to impulse, because in the end here, we're only asked to identify the forces, not the impulse. We know that they're going to be the same. They have to be the same values, which means the answer has to be D. Now, why are they pointing in the direction that they are? Well, because they're both positive. It doesn't matter that one is a +2 and one is a +7. They both exert an equal and opposite force on one another. Number 2 pushes number 1 this way. Number 1 pushes number 2 this way with the exact same force. Now, if they're different masses, they won't necessarily move the same. Okay? The heavier one would move less than the light one, but the force acting on them both would be the same regardless of whether one's heavy, one's light, whether they're both the same mass, both the same charge, doesn't matter. Okay, so the answer for that one is D. Numerical response. We started off with a pretty easy numerical response one here. Electric field, a distance of 4 centimeters. We circle that because we want to remember to convert that to meters. From this point, charge is what? It's a straightforward producer equation. E is equal to KQ over R squared. So make sure you make R 0.04 and square that as opposed to just 0.4 or just 4. The answer there for number 1 works out to be 6.47 times 10 to the 7 newtons per coulomb. And we're going to express that as 6477. Right? Multiple choice 2. A positively charged rod or object is brought near to, but does not touch, one end of a neutral metal rod on an insulated stand. Here's my neutral metal rod. Here's my positively charged object. Bring it nearby. Now, this positively charged object has a ground wire attached to it. When we bring that positively charged rod nearby there, what happens? What happens to the protons, first of all, in the neutral object? That's the easy part of it, right? Cool? Nothing. They don't move. Good. What happens to the negatives? Negatives are going to be attracted to that, right? So the negatives are going to be pulled to the right-hand side. But then we're also going to get more negatives up from the ground, pulled up in there from the ground. We cut that ground wire. Then we take this away. Well, the object is negatively charged, and the electrons have no way of getting back to the ground. So the answer is going to be D for number 2 as well. 3. The net electrostatic force on sphere 3 that's caused by charges 1 and 2. Well, I think this is pretty important, actually, to start circling these. You can see that there's 4 options here, but really there's 2 answers, 6.99 and 10.6. Okay, we got 6.99, and then we got 6.99 times 10 to the minus 4. We got 10.6, and then we got 10.6 times 10 to the minus 4. Or 1.06 times 10 to the minus 3. So basically what they're saying here is, look, this one or this one, you forgot to convert units. This one or this one, you forgot to convert units. So don't forget to convert units. That's the moral of the story, because odds are your answer is going to be there if you forget to convert units. Right, Kenton? Yeah. So let's draw the free body diagram first of all. Trying to find the force on sphere 3. It's going to be attracted to sphere 1. Because it's positive, and sphere 1 is negative. It's attracted. Sphere 3 is going to be repelled by sphere 2 because they're both positive, and positives repel each other. So we got one force to the left, one force to the right. You can get both of those forces, K, Q1, Q2, over r squared. Don't forget to make this 10 to the minus 6. Don't forget to make this 10 to the minus 2. Don't forget to square the distance. And we do all that. We get f1, we do the same thing, we get f2, and then we add them together. But when we add them together, we have to make f1 a negative value. The answer is 6.99. C. If you added them together, made them both positive, guess what? You get D. So the option is there. If you make that simple little mistake, Joey, that simple little mistake, the answer is there. So be careful with that. Okay, so now we have 3 charges. Once again, on insulated stands. Hey, they like that insulated stands thing, right? All they're telling us there is that, look, we don't have to worry about electrons being drained off of, sphere L into the ground, or coming up from the ground into sphere K or whatever. We don't need to worry about any of that. Now, honestly, you probably wouldn't have thought of that happening anyways. So even if they didn't say insulated stands, you probably would have been okay. But the fact that they do say insulating stands, they're just giving more information for those people that tend to overthink things. Okay, people that look at this and say, oh, wait, okay, I got charges here, but could they go down into the ground? No, they can't, because it's insulated. Yeah, go ahead. Yep. All right, sphere K is plus 3x, whatever x is, negative 5x, whatever x is, and plus 2x, again, whatever x is. We want to find the net force on sphere L due to K and M. Well, K and L are attractive force because they're opposites. So we're going to say the force of K on L is to the left. The force of M on L is also attractive. Which way is it going to act? L is going to be attracted to the right. Now, is that force of M on L bigger or smaller than the force of K on L? In other words, do we draw it like this, or do we draw it like this? Like that? Why? How do you know? Good. Good. The only thing different in the equation to solve for FKL and FML, and we don't know all the numbers, but the only thing different in that equation would be the value of the second charge. Okay, here it's 3, here it's 2. Bigger charge, bigger force. So we should draw it like that. That means the net force here is to the, it's acting to the left, right? So the answer is going to be A, to the left of the page. Now, this next question, this is the one that I really like in this scenario, question number 5. At point P above the sphere, the direction of the net electric field is going to be mostly what direction? Field, the net field. Well, the field goes away from positive. So we've got a field caused by K pointing this way. M is going to go this way, away from M, and it's going to be a little bit smaller. Not much, but it's going to be a little bit smaller because the charge causing it is only 2/3 the value. What about the field caused by L? Well, it's going to point downwards, right? How's that going to compare in size to the other ones? Andy? It's going to be way bigger, isn't it? It's going to be a lot bigger for 2 reasons. It's going to be a lot bigger for 2 reasons. 1, because it's closer. 2, because it has a bigger charge. So both of those factors give us, combine to give us a dramatically bigger electric field pointing downwards. Now, which one matters more? Okay, you said distance. You said they're closer, that's going to affect the electric field. You said the charge is going to affect the electric field. You're absolutely correct, both of you. But which one matters more, the charge or the distance, Cole? Why the distance? Good, because it's squared. That's the big thing right there, right? It's a squared relationship as opposed to a linear relationship like Q is, okay? As distance goes down, the force or the field goes up exponentially as opposed to linearly. Okay, so R matters more, but Q matters as well, and both of them are both of them contribute to it being a much bigger field there, which means that the answer is going to be D toward the bottom of the page. Six. Okay, here we're touching these spheres together in 3 different steps. First of all, here, let's get rid of this. We're first of all touching K and L together, then we're touching K and M together, and then we're touching L and M together. We start off with what? Well, K has a charge of 3, L is -5, M is +2. Okay, it's got X after it, but it doesn't really matter about that, right? X can be anything. Coulombs, microcoulombs, a number, 74. Doesn't really matter what it is. When we touch K and L together, they're going to balance out to be what? 3 plus -5 is -2, divided by 2 is -1. M stays the same. Now let's touch K and M together. -1 plus 2 gives me 0.5 and 0.5, and this one stays -1. And then finally L and M together. -1 and plus 0.5 gives me -0.25 and -0.25. So we look at our options here. For 0.5, -0.25, and -0.25, the answer is going to be D. Now, one person in the last class pointed out that you really, for this particular question, didn't need to go through that process. And I didn't notice that as I assigned this question. And we have to be careful because there's times when the little shortcut that this person took doesn't work. Because maybe you get a couple different options in there. But in this case, it does. This person said, I didn't do it that way. I just said, look, L and M touch each other last. So they have to be the same charge. And the only option with L and M being the same charge is D. That works. Has to be. Now, if C also had L and M the same charge, let's say -X and -X, well, that doesn't make C correct just because they're the same charge. Right? If it's the only one where they have the same charge, it's got to be correct. But know how to go through the process. But if you spot a shortcut like that, that's okay to take that. Numeric response 2. 2 parallel plates 3 centimeters apart. Again, centimeters. How many of you guys, as you were going through this, circled centimeters and microcoulombs and stuff like that? Not very many of you? Okay, a few of you, I guess. Hands are slowly going up. I don't know what it is with you guys. I don't know what it is with students. Sometimes people just don't trust me. I'm telling you, trust me. Circle these things, okay? Underline these things, okay? It leads to less mistakes. If you're okay with making mistakes, then do what you want. If you don't want to make mistakes, then do what I want you to do, because you're less likely to make the mistakes when you do what I want you to do. Circle those, underline them, highlight them, whatever. I don't care, but draw attention to them. All right, 3 centimeters apart, that's going to be delta D, right? This is between the plates. There's an electric potential difference of 44 volts between them. That's delta V. We're looking for the electric field. Where does that 1 centimeter come into play here? Here's my plates. The field strength here is 10. The field strength here is what? 10. The field strength everywhere is the same in between those plates, right? So it doesn't matter whether you're 1 centimeter from the positive plate or 6 centimeters from the, well, not 6, but 1.5 centimeters from the positive plate. The field strength is the same. In other words, the distance from the plate doesn't matter. It's irrelevant. We're going to say 44 divided by 0.03. We do that math. We end up getting 1.47 times 10 to the 3. We're going to express that A, B, C, D. 1473. Hey, this is the second time in this assignment that we've seen the A decimal BC times 10 to the D. Okay, I told you yesterday, the day before, that that's the more common way of asking them now. Okay, they used to ask B times 10 to the W. What's the value of B? Okay, they still do occasionally. If they did, then the answer would simply be, for B times 10 to the W, 1.47. Okay, be prepared for that. But usually it's the way that was asked here. These are newer questions. The questions on this practice test were taken from newer exams. So that seems to be the trend, the way they ask these questions. Oh, here we go. I like this scenario here, the 2 or 3 questions that go along with this. Here's 2 charges. The first one is positive, and that's all we're told. We want to know something about the second one, sphere Z. Well, let's not even look at the question right now. Let's not even look at the question. We know that sphere Z is attracted to sphere Y, right? Well, then what's it got to be if it's attracted to sphere Y? What's it got to be? Could it be positive? No. Could it be negative? Yes. Could it be neutral? Could be. Okay, it could be negative or neutral. So let's say negative, neutral. We figure that out without even knowing what the question is. What else do we know? Sphere Z seems to be attracted more. Does that mean the force on sphere Z is bigger than the force on sphere Y? No. It's got to be equal and opposite forces, right? We've seen that already on this assignment. If object X applies a force, object Y applies a force on Z, Z applies an equal and opposite force on object Y. What would be a pretty good explanation, perhaps, as to why Z was deflected more if it's the same force acting on Z as it is on Y? Mark? Yeah. Something with a lighter mass is going to be attracted more given the same force. Let's look at our questions here. 7. Which of the following conclusions comparing either the charges present on Y and Z or the masses on Y and Z is supported? Well, we just did that, right? Mark just answered that question without even knowing what the question was. He said that sphere Z has to be lighter, or in other words, sphere Y has to have more mass than Z. Same force, got to have more mass if it's going to be not deflected as much. 8. Hey, we already answered this question as well without knowing what the question was. The nature of the charge on Z must be either negative or neutral. The answer would be D for that one. And then, here's a good one. This is a little bit like that multiple choice question we did in class. Remember where we had the hanging charged sphere and there was an electric force that we had to find, but we couldn't use KQ over R, KQ1, Q2 over R squared. We had to use a vector analysis. Remember that? That'd be a good question to go back and review, by the way. Be a real good question to go back and review over the weekend. That question that we did on the one day in class from your multiple choice book. This is similar to that, except that we're not asked to actually calculate a force. Here, we're just asked to draw a free body diagram. So let's do that without even looking at our options. Sphere Y will be attracted to Z. If Z is attracted to Y, then Y is attracted to Z. That's an electric force. There's also a force of gravity acting down. And there's a force of the rope or tension acting up this way. There's my free body diagram. Which one matches up with that? A. Here's another one, variable value changing, right? Expect to see this on your exam on Monday as well. Okay, variable value changing. Good chance that it'll be in the context of Coulomb's law, right? Because we get that KQ1, Q2 over R squared. And it's that R squared that messes people up. Right? So good chance you'll see it in that context with the R squared on Monday. My original force here is KQ1, Q2 over R squared. This is what I start with. My new force, this is what it becomes after I make my changes. All we're doing here is changing R. KQ1, Q2 over, we're doubling the distance. So you got to square that as well because we're squaring distance. No, we're not squaring R, we're squaring distance. It becomes 1 over 4 KQ1, Q2 over R squared, or 1 over 4 times the original force. A is our answer. Next question, number 11. Okay, another good one here. The electric field strength that's sufficient to suspend a proton. That's a big word, suspend. Hey, so is this actually. because we're used to dealing with the electrons, so I'm going to draw attention to that. Want to suspend a proton. A number of people came to ask me about this question over the last couple of days. And the question that I had for them was, what does that word suspend mean? What does it mean when I say suspend? Get something suspended. It's going to stand still. It's not going to move up or it's not going to move down, right, John? It's not going to move up or down. That means that something's got to be balanced. Forces have to be balanced. People got that. As they asked me a question and I was answering their question by asking more questions, they got that. Forces have to balance. But then my next question was, what forces? Well, everybody said gravity. And then people were kind of like, I don't know what the other force is. Is it the electric field? No, that's not a force. Fields can't balance forces. Fields can't even balance fields. Forces balance forces. So we've got a force of gravity acting down. What other force has to be acting to counter this, to balance this? Yeah, the electric force. It's going to be the same value. That means that Fe equals Fg. That means that Q times E equals M times G. And we're solving for E. So it becomes E is equal to mg over q. Okay, make sure you use the mass of the proton, the charge of the proton, and when you do, you get D, 1.02 times 10 to the minus 7. 12. What's the field caused by B? Somebody came to me yesterday about this question. Said, I think I know how to do it, but I'm not getting any of the answers there. And so I did the question. I did the question right in front of her. And when I did the question, I got the same answer as her. Not even looking at hers, I got the same answer as her on this question, and it wasn't even there. And then we figured, oh, this is what we did. This is what both of us did. Just happened to be a coincidence that both of us did the wrong thing. We were both in radian mode. Here's the good news. If you're in radian mode, we don't want to be in radian mode, right? You want to be in degree mode because that's a big time waster. But if you're in radian mode, the answer's not going to be there. Okay, you don't need to worry about, oh, I do it in radian mode, I forgot to convert, and they're going to trick me by putting that option there. They're not going to do that. Okay, but you still got to do the question again. So we want to avoid that. In the end here, we get the field caused by A, the field caused by B. The field caused by B is upwards. It's the Y component of that electric field. So all we're going to do here is say, look, sine 71.3 is equal to opposite over hypotenuse. So Y is equal to 0.47 times sine 71.3, which for number 12 works out to be C, 0.45. $13. Or 3, I should say, I guess. This is like, this is what we've been doing the last couple of days, right? We got an alpha particle here, which I'm going to circle that in red because I'll probably make that the charge of an electron or something. If I don't. An alpha particle slowing down. That's like a car doing what? We're stopping it. That's like a car going up a hill. When a car goes up a hill, it's a conversion of energy from kinetic to potential. It's 1/2 mv squared that goes to mgh. But this time we're going to sub in qv for mgh, right? Because that's what we do. It's the same thing, except it's electric potential instead of gravitational potential. Now, we're looking for the initial kinetic energy. So we don't even need to put in 1/2 mv squared. If you recognize that right off the top, then you could just say the initial is EK. EK initial is equal to QV final. And when you multiply those two numbers together, make sure you make Q 3.2 because that's the charge of an alpha particle. We end up getting 9.12. Now, here's one where it's not A decimal BC times 10 to the D. We're just looking for the base there. Okay, we're looking for the blank, 9.12. Basically, that's the same as the ones that say B times 10 to the negative W. 13, almost done here. You want to find the acceleration of this guy right here. Well, let's find the force that acts between them. It's KQ1, Q2 over R squared. Now, I don't know what that force is because I didn't write it down here. But whatever it is, we can find it pretty easily, right? Whatever it is the force on number 1 and it's the force on number 2. It's the force on both of them because if object A applies a force on B, then object B applies an equal and opposite force on object A. It's the same force. Now, if we want to find the acceleration of object 1, we're going to take that force that we just found and divide it by that mass. If we want to find the acceleration of this one, we're going to take that force that we just found and divide it by this mass. We only need to find one of those accelerations. But if we found both of them, if we were to find both of them, which one would be greater? The acceleration of sphere 1 or the acceleration of sphere 2? Which one's a bigger acceleration? John? Good. 2 because it has less mass. Same force, but bigger acceleration because less mass. Now, we're not asked that question, but we could be sometime. We're asked what is the actual value of that acceleration. Take that force that you just found, divide it by that mass that's given to us there, and when we do that, it works out to be C, 9.59 times 10 to the minus 2. Felt a little guilty about giving you this question, at least at first. Then I got over it. It's a challenge question. In fact, almost a trick. Almost. Which of the following graphs represent the relationship between the electric field and distance from a point charge? If those were all covered up, if those options were all covered up, I would just automatically say this. Right? Because E is equal to KQ over R squared. It's an inverse square relationship. It should look like that. But look at that. None of those options are there. Which one can we eliminate right away? With what we have up on the board right now, which one can we eliminate? Colin? B. Okay. If E versus R is supposed to be curved downwards, well, then it's certainly not going to be a straight line. So that gives us a 33% chance now. This relationship, we learned this, right? This relationship tells us that the electric field is equal to something times 1 over R squared. It's an inverse square relationship. The reality is, if we saw this graph, we can't analyze this graph numerically. So what we would actually do, and you don't have to actually do this on an exam because it's multiple choice. So if we were to analyze, and we will do a question similar to this later on where we do have to actually go through this process, but just as practice, we'll do it. We would have to straighten it out. We would have to turn that graph into a straight line graph by doing something to this variable right there. Well, what do you think it's going to be? What do you think it's going to be? Okay, if we want to make this into this, what does this variable have to become? It comes from our equation, right? We're going to take all the values of R and then calculate 1 over R squared. Why 1 over R squared? Look. Okay, E is equal to something times 1 over R squared. In other words, look, Y is equal to M times X plus B. Okay, whatever this is the slope of that graph. That make sense? So the answer would be what? D. Yeah. That's a tricky question. Okay, that's a tricky question. I think you can handle that though. Okay, that's one of those ones you got to think for sure, and even go next step, even that next step beyond the regular thinking, and say, okay, here's the relationship. Okay, we've done this the other way around. Okay, plotted the graphs, but never have we looked at the equation and said, oh, all right, y, yeah, okay, it's got to be the x-axis. If this is the y-axis, okay, then this has to be the x-axis, 1 over R squared. 15. Which of the following statements describes the relationship between the forces described by Coulomb's law and the forces described by Newton's law of gravitation? In atoms, gravitational forces are weaker than forces. Somebody came to me a couple days ago and said, I'm kind of thrown off by that word in atoms. Okay, we said in class that generally gravitational force is weaker than electric force. Well, then why are we thrown off? If in general gravity is weaker, well, then in atoms, gravity is weaker. Even if we've never mentioned it in the context of atoms, okay, we have mentioned generally, okay, we've given you a bigger answer than this. Okay, generally, not just in atoms, but usually for everything, the electric force is stronger than the gravitational force. So this is going to be our answer. Let's just take a quick look at the other ones, though. Gravity and electric force are attractive? No, because electric can be repulsive as well. Gravity acts at any distance. Electric force acts at very short distances. No, they're both related to distance the same way. So if one's very short, the other one's very short. If one is longer distances, then the other is too. As the distance increases, electric force increases. No, as the distance, as the distance increases, the electric force decreases, same as it does for gravity. Okay, it's the same relationship. So sure enough, the answer does happen to be A. Last question. Finish off with a pretty straightforward one. The field caused by the first one is away from it. Caused by this one is towards it. The net field as a result of both of those two is this way. So the answer is C.